Good morning, everyone. I'm Chen. My thesis topic is about complete flow description from combination of incomplete measurements, and my supervisor is Stefano Dicetti and Marco Raola. And as we know, the pressure field in the fluid flow is very important in locating the noise source and scientific research and calculating the unsteady pressure flows on vehicles. And traditionally, the direct measurement of pressure are majorly done by the probes, which is mostly point-wise, but we can have an indirect way to estimate the pressure by the Navier-Stokes equation, where the pressure gradient is a function of velocity field. And then we can calculate the pressure by integrating the pressure gradient. And as we can see here, there are temporal. As we can see here, there are temporal derivative and spatial derivative of the velocity, and the PIV can provide the spatial derivative of velocity naturally because they are space-wise, plane-wise or volume-wise measurement, but the time derivative of velocity requires the snapshot of velocity field to be close enough, so they are time resolved. And the restriction of such high-speed PIV is that it requires high-speed laser and cameras. There are two branches of the pulse laser that we often use. One is NDYAG, which has the typical frequency up to 15 Hz, and NDYLF, which has typical frequency up to 10 kHz. And also there are two branches of cameras. One is for low-speed PIV measurement, and another is for high-speed PIV measurement. And the handicap of the low-speed PIV system is that they are more expensive, and the energy of NDYLF laser has lower power in each pulse, and the high-speed camera are often less sensitive. And finally, even we have such fast PIV system, the upper limit of the measurement speed velocity is around 20 meters per second, which is still not very high. So our objective is to steal the time resolution from the probes by combining the measurement from snapshot PIV, which has lower frequency, but is easier to be done, and the fast probes. Then we have the time-resolved flow field, and the pressure can be directly estimated from the time-resolved flow field. And there are some methods to bypass the time derivative in Navier-Stokes equation. One is to take the diversity of the equation, then it is converted to a Poisson problem, but the time derivative still exists on the boundary, so we need additional boundary conditions. And another way is to use the Taylor's hypothesis, where the time derivative of the velocity can be estimated from the mean and fluctuating velocity, but it's not endurable for a long time. And another way is to use the vortex conservative equation like this, and it requires the volumetric velocity field or 3D velocity field, and this equation cannot consider dissipation. And our data-driven method is to, here is a video of our data-driven method. The synthetic dataset is generated from numerical simulation, and the detail is in this article. Then we generate the snapshot PIV by downsampling the original dataset, and have the probe data by set several virtual probes by the end of the domain. And then we forget about the original dataset. The data-driven method can combine the snapshot PIV and probe data and generate or reconstruct the time-resolved flow field. And to solve this problem, firstly, we want to simplify this problem. We wish the flow field can be decomposed into a time part AT and a spatial part phi x, so that the velocity field in every snapshot can be the linear combination of the spatial modes phi I here. And it's possible in mathematics. There are one algorithm called SVD here, which can split the original flow field into the temporal modes psi and energy of each mode sigma and the spatial modes phi. And after that, our data-driven method are designed to input with the probe data here and output with the coefficient of spatial modes or the temporal modes in last slide. And after training, we only need the data from probes and the time resolved flow field can be reconstructed, and their sample rate and their frequency is in the sample rate of probes. And there are two approaches of our data-driven method. One is EPOD, where we find the linear relation between the temporal modes of the probe data and the flow field. And another one is MLP, multi-layer perception, which is the simplest application of neural networks. And EPOD is fully linear, but MLP can be nonlinear by taking advantage of the nonlinear activation function inside the nodes. And there are more details about methods and techniques of EPOD in these two articles. And here is the result of EPOD and MLP. And we have the pressure directly integrate from the original data set and the pressure from EPOD and from MLP, and the error is on the second row. And here is the RMS error of the velocity and time derivative of velocity and the pressure of data-driven method EPOD and MLP, and the Taylor's hypothesis as comparison showed here. And as we discussed before, the time derivative of velocity can be estimated using Taylor's hypothesis by the mean and the fluctuating velocity. So we use the exact flow field to estimate the time derivative of velocity in Taylor's hypothesis, and there is no show here. And finally, from this case, our data-driven method prevails to Taylor's hypothesis, and MLP is better than EPOD. And another validation is on experiments in the water tunnel of UC3M, and the Reynolds number is 4800, and the sample rate is 30 Hz. Is not very fast, but since the mainstream flow moves very slowly as well, the PIV is finally time resolved. And like the synthetic cases, we have the snapshot PIV by downsampling the original datasets, and the probe data just directly extracted from the flow field. And here is the result of our experiments validation. And there are several tasks ongoing. The first one is to find the optimal sensor placement, and in our test, the finest displacement has 8% prevail to the vanilla one. I mean, the one with the sensor in equidistant. And the second one is to maintain the fidelity of the reconstruction, especially the low error and low pressure error and high pressure error here. As you know, the velocity is derivative or differentiated in the Navier-Stokes equation, which will definitely amplify the error. So it's more difficult to maintain the fidelity in the pressure than the velocity field. And here is a sketch of our data-driven method. We have the incomplete measurement, such as a snapshot PIV, which lost the resolution in time, and probe data, which is only point-wise. And after EPOD and training, we can reconstruct the time-resolved velocity field directly from the probe data and what we learned from the training session. After that, the pressure is integrated via Navier-Stokes equation, and we have the complete description of the time-resolved velocity field and the pressure field. And here is the conclusion. Firstly, data-driven methods enable successful pressure field measurement in current tests, and MMP prevails to EPOD in current tests for its capability of fitting nonlinear relations. And after training, the data-driven methods only need probe data. And I have 1 journal article published and 2 conferences participated and to participate since last doctoral meeting. And the future plan is to improve the algorithm and conduct experiments using the rare probes and doing it in 3-dimensional cases and research state. Thanks for watching.